Karnaugh maps is another way to simplify Boolean functions. It provides systematic method for simplification of Boolean functions. It gives me the lowest possible number of terms and literals. It is easy to use, but it's limited to 5 variables in the domain of the function. Let's take a look at this function, the domain of which is a, b, 2 variables. And this is equal to the min terms m0, this is m0, ORed with min term m3. Okay, this is the truth table for this function. These are the variables a, b. These are all the possible values for the a, b. And this is the output of the function. It's min term 0 and min term 3. I can represent this function and this truth table in a different form, namely a k-map. Here we have a 2-variable k-map. The k-map here consists of 4 cells. Each cell represents one case of the inputs. For example, this case here, when a and b are both zeros, is represented in this cell. This cell here represents the case where a equal to 0 and b equal to 1, which is this case. This cell represents a being 1, b being 0, which is this case here. And finally, this cell represents this condition here. Now, when both a and b are zeros, which is here, the value of the function is 1. So I put a 1 here. And when both inputs a and b are 1, which is this, the value of the function is 1. The rest are zeros. So this is the k-map for this function. You have seen this 2-variable k-map. Here we have the values of a, which is 0 and 1. Here we have the values of b, which is 0 and 1. Notice that in these 2 cells, a is equal to 1. And in these 2 cells, b is equal to 1. I can do the labeling in a different way, namely this one. I don't have to put the values 0, 1 here, 0, 1 here. I can draw it this way, and I can say from this that a here is equal to 1, b in these 2 cells is equal to 1. Also, if I have a map, a k-map like this, I can label it in a different way. Notice that here b is equal to 1, so b is equal to 1, and I put this b here. And here a is equal to 1 in this area, so I put the label here, a, meaning that in these 2 cells, a has a value of 1. Now again, in this cell, a is equal to 0, b is equal to 0, and that represents min term m0. So I can put here m0. In this cell, a is equal to 0 and b is equal to 1, which is min term 1. So this cell represents min term 1. And this here represents min term 2, and this here represents min term 3. Notice the difference between this cell and this cell. These 2 cells, they differ in the variable a. Here, b is equal to 0, b is equal to 0, while a here is equal to 0, and a here is equal to 1. So these differ in the value of a. If we take these 2, we find that they differ in b. b here is bar, and b here is without a bar. These 2 also they differ in a, and this is the whole idea in using k-maps, so that we can use unifying theorem, which says a or a bar is equal to 1. So these 2 cells, we say that they are adjacent. Adjacent meaning they differ in only one variable. These 2 cells are adjacent. They differ in only one variable. These two also are adjacent. They differ in only one variable. Okay, if we take a look at this map represents the function f or c equal to a ANDed with b, which is min-term 3. So c is equal to m3. This is the function that is represented by this map. This map here represents a function with two min-terms, namely this one where a is equal to 1 and b equal to 0, which is min-term 2, and this one here is where a is equal to 0 and b is equal to 1, which is min-term 1. So this map here represents the function s, which is equal to m1 ORed with m2. Okay, let's look at the function where we have the variables a, b, and c. We have the domain for the function 3 variables. This, of course, will need an 8 cells K-map because it has 8 min-terms. We lay out the K-map this way. Okay, here at this side we have the a here equal to 0, the a here equal to 1, and the bc variables here they are equal to 0, 0. Here 0, 1, here is 1, 1, and here is 1, 0. The reason we laid out this arrangement, it is the gray code sequence here we used, so that to make sure that the cells are adjacent to each other. Now this cell represents min-term 0, M0, and this cell represents min-term 2. So the counting is M0, M1, M2, and then here back M3, M4, M5, here is M6, and this is M7. In the 3 variable K-map, each cell is adjacent to 3 cells. For example, here, M0 is adjacent to M1, and M0 just is adjacent to M4, okay? M0 is also adjacent to M2. So there's something called the wrap around, as if we wrap this map around itself. Why is M2 adjacent to M0? Because they differ in only one variable. Here in M2, A is equal to 0, B is equal to 1, C is equal to 0. While here, A is equal to 0, B is equal to 0, C is equal to 0. So they differ in the variable B. Okay, M6 is adjacent to M2, is adjacent to M7. It is also adjacent to M4. They differ in the B variable, which is here 1 and here equal to 0. Okay, what is this K-map represent? What function does it represent? What is the function f that this K-map represent? Now, the domain of this function is ABC, so f is equal to M4, M5, M7. Where did I get M4 here? This is M4, and this is M5, and this is M7. So f is equal to the sum of min-terms 4, 5, and 6. Now, if we want to represent this function in a K-map, how do we do that? Okay, f is equal to 1 in the area where a is equal to 0, which is this area here, b equal to 1, which is this one, and c equal to 0, which is this. So we are left with this min-term here. Now, the a, b bar represents actually 2 min-terms, which are 4 and 5. Where a equals to 1, this area equals to 1, and b equal to 0. Where is b equal to 0? In this area. So the intersection between these two areas are this cell and this cell. Let's look at the 4 variable K-maps. 4 variable K-maps are for functions that have 4 variables. The function has the variables w, x, y, z. as a domain. So it consists of 16 cells because it has 16 minterms. It is arranged this way. This is the area where we have the W equal to 1. And this is the area that we have X equal to 1. This is the area where we have Y equal to 1. And this is the area where we have Z equal to 1. So here in this cell we have W, X, Y, and Z. They are all zeros. So this is corresponds to minterm M0. Here W, X, and Y, they are 0, except the Z is equal to 1. So this corresponds to M1. And this is M2, M3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and back here is 15. In 4 variable K-maps, each cell is adjacent to 4 cells. M0 here is adjacent to M1 because they differ in the Z value only. M0 is also adjacent to M4 and they differ in the X value. And M0 is adjacent to M2. They differ in the Y value. And this M0 is adjacent to M8. We say that every cell has 4 neighbors. Let's look at M11 here and see its neighbors. It is M10, M9, M15. Also, it is M3. Now, given this K-map for a function which has the domain W, X, Y, Z, what is this function? It is minterm, this one, which is 0, 2. This is minterm 2. This is minterm 5. And this is minterm 8. And this here is minterm 14. And this here is minterm 15. So the function is the sum of the minterms 2, 5, 8, 14, and 15. If we try to represent this function in a K-map, then this map is a 16 cell map which has 4 variables. Now this is the area where W is equal to 0. And this here is the area where Y equal to 0. I'm trying to find out what this term represents in the K-map. And this is the area where X equal to 1. So the intersection of all these areas is this. By following the same procedure, we can find out where this term is represented on the map. And we find out that it is this minterm, which is minterm 8, and this is minterm 14.